In this video, we're going to walk through the mechanism for how to make diazonium ions. Let's unpack that name for just a second. The infix azo really means a nitrogen. So anytime you see that, you want to think nitrogen. The A in azo means not, just like the A in atypical, or the A in atom. Atom means not cuttable. And so azo means not, and the ZO is coming from the same root as the word zoo, animal, or in this case it's standing in for life. And the idea behind this was when people were first investigating nitrogen, they investigated nitrogen gas, and they found that creatures couldn't survive, animals, couldn't survive, if they were only surrounded by nitrogen gas. And so they would die, so not life was given to nitrogen. It's kind of ironic because you have to have nitrogen in order to survive. You need it. Your cells use ammonia to make amino acids, or the cells of microbes do, and 79% of the air you're breathing right now is nitrogen gas, N2. So it definitely doesn't kill you, but if you had just pure nitrogen, you wouldn't have oxygen, and so you would die of suffocation there. So azo, from now on, whenever you see azo, for the rest of this chapter, you want to think nitrogen. And if we make diazonium ions, the ending -ium in general just means charged particles. So we're going to have a nitrogen with a charge on it, and because of the prefix di, it means we're going to have two nitrogens. So hopefully that name makes sense now. We have diazonium ions here in our product. Two nitrogens, di, so two di, nitrogens, azo, and they've got a charge on them, so they're an ion. So we want to learn how to make these diazonium ions, because this can get kicked off of that carbon chain really easily. That's why these are so useful. They can easily take this electron, get kicked off. Those electrons would help stabilize the positive charge. So you can see this is an awesome leaving group, and that will push reactions very far forward, because we just saw as N2, that is a gas. And so that would bubble away out of solution, removing your product and pushing the equilibrium to the right, toward more products, to replace the product you're removing, using Le Chatelier's principle. Anytime you can create a gas in your product, it really increases the efficiency of your reaction, because the gases automatically bubble out of the solution, remove product by them automatically, and that pushes equilibrium to the right. So that's why that's what a diazonium ion is. Two nitrogens triple bonded to each other, attached to a carbon chain, and the nitrogen that's attached has a positive charge. And that's why they're useful. They're amazing leaving groups, so we can do SN2 reactions with nucleophiles that we could only dream about before. Now, the way we can make diazonium ions is ultimately going to be from amines, the unifying functional group of this chapter. And the recipe that we'll always use is we're going to add sodium nitrite and hydrochloric acid. So this probably looks a little bit like black magic. You can see that you have two nitrogens, so those are going to come together. Otherwise, we have hydrogens that we need to get rid of. So in the back of your mind, you'd think, well, it's going to take some proton transfers. And then we have oxygens bonded to the other nitrogen that we have to get rid of. And to turn those into good leaving groups, that will also take a bunch of proton transfers. So in general, as we see this, we're going to see that this one nitrogen is going to have to do a nucleophilic attack on the other one, and then we're going to have to do a whole bunch of proton transfers in order to get rid of all the hydrogens and the oxygens. We'll walk through that mechanism step by step in this video. Because this is so significant, we're going to do so many reactions with it, it's important that you know how this is made. Now, sodium nitrite, the nitrogen source that we're going to use here, looks like this. These white crystals here are galaxies of sodium nitrite molecules. And hydrochloric acid, which is the acid that's produced in your stomach. This is, it looks like this. Here it's just a clear liquid. So in your first step is a proton transfer. Now, if you look back at the recipe we have, you start with sodium nitrite, NaNO2 and HCl. NaNO2 looks like this over here. Nitrogen forms 3 bonds, 2 to one oxygen and 1 to another. That oxygen that only has a 1 bond will have 3 lone pairs and a full negative charge, which is being stabilized by the sodium. You could see how that oxygen would be interested in a very acidic proton on HCl. So you do a proton transfer. The oxygen steals an H plus from that, and the electrons in that bond snap back onto the chlorine. Now the chlorine ends up going its own way, and the nitrite ion ends up accepting this H with its plus charge, so that we have this here. The oxygen accepted the H and a plus charge. It had a negative charge before. Once it accepts the plus charge, it's neutral. So we have this molecule here. Now ultimately what we're trying to do is get rid of these oxygens, right? If you look at the overall picture of what happens, we don't have any oxygens bonded to those nitrogens. So the oxygens bonded here need to leave as leaving groups. So we're trying to turn this oxygen into a good leaving group. Well, we definitely made it a better leaving group by putting 1 hydrogen on. We can make it into an even better leaving group by putting a 2nd hydrogen on. So we can do a 2nd proton transfer. The oxygen here is slightly negative, the chlorine is slightly negative, and the hydrogen is slightly positive. So the oxygen can very easily swoop in, steal that hydrogen, the electrons that were holding it to the chlorine snap onto the chlorine. And what we get after that step, the chlorine leaves, lives its best life. What we get after that step is an amazing leaving group. So notice, compare. After this oxygen accepts this hydrogen, it has 2 hydrogens and a full positive charge. It has 3 bonds, and so a full positive charge. And what we have here is an amazing leaving group. Because if that takes these electrons and leaves, the electrons will just stabilize its positive charge. It'll be neutral. It'll be water, a very stable molecule. And so it's very likely to pop off the molecule. And here we're detaching our first oxygen from the nitrogen. That oxygen leaves, it's loss of a leaving group. And what we get is something called a nitrosonium ion. So compare. This is what we have left down here. Now, this nitrogen lost these electrons, and so it has this positive charge, and that gives us one of the 5 resonance structures. We have a lone pair next to a positive charge. And anytime that happens, so now we know we have resonance. To get the other resonance structure, you move the lone pair toward the positive charge to create a pi bond. So what we create here is this other resonance structure. So this lone pair comes down, there's only 1 left. We started with 2 pi bonds, we end up with 3, and the positive charge moves on to the oxygen in the other resonance structure. Remember, these brackets tell you that the true structure is neither of these, it's only the average between them, and the special resonance arrow with 1 line and 2 heads means take the average. It does not mean that these are turning into each other. Neither of these structures ever exists. Only the average ever exists. And it's that resonance that stabilizes this, because otherwise a positive charge on an electronegative atom is very unstable. Even so, we do have a slight positive charge on the nitrogen, and so this is where we open up an opportunity to create the nitrogen to nitrogen bond. Never lose sight of what we're trying to do. We're trying to create a triple bond between 2 nitrogens. We just removed one of these oxygens. We turned it into a leaving group with 2 proton transfers, and then it left as water. And now this other nitrogen has a positive charge. That makes it an electrophile. And the lone pairs on the first nitrogen can attack it as a nucleophile, and that can give us our first bond between the nitrogens. So here, the lone pair here can swoop in, attack the positive nitrogen, and we would have this structure down here. So if you're trying to make connections, this is here, and this nitrogen is this one here, with the 2 hydrogens on it and a carbon chain, the R group. And because it has 4 bonds, it has a full positive charge. Well, we want to stabilize that. So we're going to do a proton transfer. Water can come in And this water is we've made in the previous step. This was our leaving group in the third step here. That water can come back and do a proton transfer. The slightly negative oxygen can steal the slightly positive hydrogen. The electrons snap back onto the nitrogen to stabilize the positive charge. And now we have this molecule here. So notice we still have the nitrogen double bonded to the oxygen. That stays the same. The only thing that changes is the nitrogen doesn't have that hydrogen anymore, and it also doesn't have the positive charge. In the process, this oxygen has accepted a hydrogen and the positive charge that comes with it. And so we have hydronium. Now, we have the two nitrogens attached, and they're stable. But we still want this oxygen to leave, and we still want this hydrogen to leave. That's going to involve several proton transfers. In the most recent step, we made hydronium. We can turn this oxygen into a good leaving group just like we did for the first one, by doing 2 successive proton transfers, turning it into a water, and then it just easily, with a quick push, comes off. So the slightly negative oxygen can steal the slightly positive hydrogen here. The electrons snap back onto the oxygen there. And now, that turns into, this oxygen has a positive charge because of the hydrogen we just added. Everything else has stayed the same. The nitrogen, for example, in that step. Okay. Now, in this next step, the hydrogen on the nitrogen is going to leave. And we're going to form a double bond here. So this oxygen is really trying to steal the electrons in the pi bond. It's very electronegative, and also more electronegative than nitrogen, actually. It's to the right of it on the periodic table, and also it has a full positive charge to steal electrons with. So the electrons want to go towards it. And so water here can act as a base, steal this slightly positive hydrogen. This can go toward the other nitrogen, and that kicks these pi electrons up to stabilize that positive charge. So ultimately we're doing a proton transfer. We're taking this hydrogen and putting it onto a water molecule. What we end up with after that step is, notice we only have a single bond now between the nitrogen and the oxygen, and we have a double bond between the two nitrogens. So we're inching our way closer to our ultimate goal, which is to have 3 bonds between the nitrogens. And we're doing that really with a lot of proton transfers. Okay. Well, we want to get, we have all the hydrogens off this nitrogen. We just want to get this oxygen off of the other nitrogen. And so we need to turn it into a better leaving group. And we can do that with another proton transfer. This can accept one of the slightly positive hydrogens on hydronium. The electrons snap back onto the oxygen. Right? This hydronium that we made in the previous step can now act as an acid and give this hydrogen back at a different place, so that ultimately, here's our bond there, so that ultimately what we have is a good leaving group. We have a water there that can act as a good leaving group. And so that's what it does. All it needs is a little push, and it gets that push from these electrons on this nitrogen. Right? Here, if you're looking at this, the nitrogen is less electronegative than the oxygen, and the oxygen also has a positive charge. So the electron density is really moving there, and a kind of unusual thing is happening. The nitrogen has a slight positive charge on it. And so this lone pair is attracted to that, and it moves over and kicks this good leaving group off. So you have loss of a leaving group, and we end up with our diazonium ion. Our diazonium ion. So a quick recap. We did a proton transfer. We started out with sodium nitrite. The nitrite has 2 oxygens bonded to the nitrogen. The negative oxygen steals a hydrogen from HCl twice, so that it turns into a good leaving group, and then it pops off. and we have our nitrosonium ion. That gets attacked by our other nitrogen, the nitrogen that we want to attach to this first nitrogen. So nucleophilic attack. And then you want to stabilize the nitrogen that came in by doing a proton transfer because it has a positive charge. At this point, we need to remove the hydrogen and the oxygen. We can remove the oxygen first by doing a proton transfer, just like before, and the hydrogen by using the water that we make in this step. That gives us this molecule here, where we can create the two bonds between the nitrogen. Now we just need the oxygen to leave, so we do another proton transfer. Now it's a good leaving group, and with a little nudge from the lone pair on the nitrogen from the amine, the leaving group comes off, and we have our diazonium ion, which is very useful. So in the big picture, we turned an amine into a diazonium ion by adding sodium nitrite and HCl. This is going to be an amazing leaving group that produces really efficient reactions because it bubbles away as a gas. And we'll be able to use nucleophiles and attach nucleophiles to carbon chains that we wouldn't even have dreamed of before, or that we could only dream of before, by first creating these diazonium ions from an amine. So this video walked through the mechanism for how that was made. In a future video, we're going to do some synthesis. Think about this reaction from the perspective of chefs, from the perspective of synthesizing molecular dishes.